A very good evening to everyone. On behalf of Nehru Planetarium, Nehru Memorial Museum and Library, myself Prerna Chandra working as Program Manager, welcome you all for joining in for today's discussion, which is about the fantastic bursts and how to find them. Fast radio bursts, FRBs, are quick and unpredictable flashes in the sky coming from incredibly far away outside the galaxy object. To detect this FRBs, astronomers survey both swaths of sky and have to mutually search for a new real signals among thousands of false signals. Detect every day. Artificial intelligence here play a vital role. It's being used to automatically detect the FRBs among the haystack of false signals. Today in this discussion, we will be discussing the how artificial intelligence peeping into the cosmos. To talk on the subject, we have a very special guest with us, Dr. Devansh Agarwal, data scientist at Bristol Myers Squibb, New Jersey, USA. I welcome Dr. Devansh for joining in for today's discussion. Dr. Agarwal is PhD in physics and astronomy from West Virginia University, and presently he is working on the intersection of machine learning, high performance computing, and big data. Planetarium welcome you, Devansh, and also would like to mention that he is a dear student of late Dr. N. Ratnashri. She will be proud there seeing her student doing so much well in their related fields. Welcome you.
Thank you. So let's get started. So if you can just let me know if you are able to see my screen.
Yes, we can see that.
Okay, sounds good. Well, thank you, planetarium staff and Megha for organizing this. I'm Devansh. I presently work as a data scientist, as mentioned. I've just finished my PhD last year, working on fast radio bursts, and this is what I'll be talking to you about today. This is what I term them as fantastic bursts, and we'll be talking about how do we find them, and how we are using artificial intelligence today to sort of find more and more of them, and why they are important as well. So this talk is being organized in memory of my mentor, late Dr. Ratnashri. So about a decade ago, I came to the planetarium when I was doing my BS and MS at ICER to work with her on a project which started on pulsars. I won't be talking about pulsars today, sadly. But this is how I started, and then I sort of ended up doing a PhD in radio astronomy and sort of continuing that in the background still. So today, we'll start our discussion by talking about the electromagnetic spectrum. So this is all the light which we see and the light which we do not see by our eyes, but we have other instruments and methods to see them. We'll be talking about how different astronomical objects like galaxies look in different parts of the electromagnetic spectrum. We'll see what telescopes we use to see them, but in particular, we'll be talking about just radio telescopes because we'll be only talking about one specific part of the spectrum. Then we'll finally come to FRBs or fast radio bursts or these fantastic bursts. And I'll try to convince you by the end of the talk that these bursts are indeed fantastic. And then here's why they are so. This is how they look like. This is a kind of plot which you will see a lot today, and I'll try to explain what's going on over here. There's a huge variety of FRBs or fast radio bursts, so we'll step through that for a little bit. And how do we find them actually? How do we find a real astronomical signal as opposed to all the noise which is present out there? How we use AI, this is convolutional neural networks, to help us out in this program. We'll be talking about a particular program which we made, which it's called Fetch, which helps us distinguishing between this real and bogus signals. And then what's the present status? What's the current scenario look like? Where we are in terms of fast radio bursts? How many do we have? And what are all the telescopes in the world doing to find more of them? And sort of completes the whole loop. So to get started, the first thing I'll show you is the prism. And this is what a cartoon drawing of a prism looks like. And what it does is you start with your white light on the left side, and it splits it into its multiple colors, the VIBGYOR as we have seen it. So this is what our usually prisms do. And this is what constitutes our electromagnetic spectrum, part of electromagnetic spectrum, which is called the visible light. So which is what we know of, which is what we see every day. Now, this is a very small part of the whole spectrum, which is available out there. So on the left hand side, you have very short wavelengths. These are cosmic rays and then gamma rays. And on the very right hand side, you have long wavelengths. So this is all starting from infrared going till radio waves. So we will be mostly talking about radio waves in this particular talk here today, and especially the ones which are somewhere around a meter or so. So this is where they usually lie. Now, uh, most of us have seen pictures like this. This is the Andromeda galaxy, as you see with an optical telescope. This is bright and colorful, but this is only one part of the spectrum. This is only optical or visible light. Visible light found using optical telescopes. So you can use other telescopes which work in different regimes of electromagnetic wave and see how this galaxy looks like. So this is what it looks like in visible light or optical. If you go to X-ray, you can see very different features over here. You can see that the center part of the galaxy is much more brighter, but the outer parts are not that much bright. If you go to IR or infrared, there's a different picture. If you go to radio, there's a whole other picture, and so on. And the reason this is important is because different wavelengths of electromagnetic spectrum of the same object give us different information. So it's like it's so we use all this multi-wavelength information to create the complete picture or to understand these objects better. Now, if you go to a place which doesn't have a lot of light pollution, your night sky might look like this. Again, this is electromagnetic. This is just the visible part of the electromagnetic spectrum. So this is how it looks like. But the radio sky, if you look at through a radio telescope, is going to look very, very different. So this is how it looks like. So this is a picture made at the Green Bank Observatory here in West Virginia, US, and this is what it looks like if you had radio eyes. So now we'll start moving towards radio telescopes and what they and these are going to sort of form the heart of this talk. So we use these large, giant parabolic dishes, as shown over here. On the left-hand side, we have the Green Bank telescope. So this is a huge dish. This is about 110 meters in diameter. On the top over here is the Arecibo telescope, which sort of sadly uh, is no more because this platform fell off. But this was a 305-meter telescope in Puerto Rico. And below here, we have an interferometer. So this is a Y-shaped instrument, which is made up of about 30 or 20, 25 to 30 small dishes, which are much smaller as compared to this, but you can use cool sort of signal processing tricks to simulate like a huge dish, which is about several kilometers wide. Now, in this talk, most of the data has actually come from the Green Bank telescope. So this is world's largest fully steerable telescope. It's heavy, it's incredibly heavy, and it's incredibly large. And it runs for about 6,000 hours every year. So most of the time, it's always observing. Daytimes is sometimes reserved for maintenance, but it sort of keeps observing day and night all year long. And it observes on a huge range of frequencies. So it observes at about from 1 gigahertz to about 100 gigahertz. So it also covers a huge range, gives us a huge range to study, which allows us to study the multiple objects at the same, which allows us to study the same object at multiple frequencies, giving us a wealth of information which we can sort of pull out. Now, now I'm gonna sort of shift to lightning, and I'm gonna convince you that lightning is also related to all this. So the funny thing about lightning is that you can actually observe lightning from the other side of the earth if it's happening on one side. And the way it happens is that we have these magnetic fields of earth, and the lightning, which is a flash, which is just a flash of light, has electrons which can actually travel through these which can actually travel through these magnetic field lines. So this is a very well-known phenomena. You can actually detect lightning on the other side of the earth. Now, what also happens when you see lightning on the other side of the earth is a phenomena called dispersion. So the uh, the magnetic field lines also contain electrons, and whenever this electromagnetic wave or the lightning flash travels through this loop of magnetic field which has electrons, what happens is higher frequency waves arrive earlier as compared to the lower frequency waves. And the reason, or this phenomenon is called dispersion. This is the same thing which happens when you pass white light through a prism, that the higher frequency waves travel faster as compared to lower frequency waves. So what happens is you see a delay between the highest frequency and the lowest frequency. And if you actually look at it, it looks like this. So this here on the x-axis in this graph is time. On the y-axis is frequency. So the top part is higher frequency, the lower part is the bottom frequency. And this is a small video which actually also converts this whole signal into audio. So let's see if it actually plays. Yep. Uh, so I have Okay, so I hope you could hear this, but what's happening over here is that, so as you can see, the more red the color is, the more sort of strong the signal is. And what's this swish thing which you're seeing over here is just higher frequency waves arriving earlier as compared to lower frequency wave. And this whole thing is just called dispersion. So your electromagnetic waves, whenever they pass through some ionized medium, for example, a medium which has electrons in it, they will undergo dispersion, similar to what you see in a prism. When your white light passes through a prism, it sort of separates into its 7 colors. This is exactly the same phenomena over here. Higher frequency waves arrive as compared to lower frequency waves. So this is called dispersion, and this is all related here because when we start observing these cosmic flashes, these fast radio bursts, this is the first which you will see, and this is how we actually know that these are astronomical objects. So this is what it sort of looks like. You have these switches over here, higher frequency waves arriving earlier as compared to lower frequency waves. And now we come to the topic of fast radio bursts, or FRBs. This is an artistic sort of artistic representation of what FRB sort of looks like. You have a radio telescope. In this case, it's the Green Bank telescope. It's pointing somewhere in the sky, and then there's this cosmic flash which happened, and then you are receiving it on your telescope. There's another one which is again similar. You again have the Green Bank telescope looking at some part of the sky, some cosmic flash going on, and then your sort of telescope receiving it. This is not exactly how it looks like in real life. This is just an artistic imagination of the phenomenon. Now, so how does exactly this FRB thing work? So somewhere in the galaxy, we are sitting over here. So we have our own Milky Way sitting at the bottom. We have this thing called the host. We don't know what host is. So this is a place where the FRB is happening, somewhere outside our galaxy. Okay, this is where we are on Earth, here at the bottom. And then the host emits this cosmic flash, this fast radio burst. So this is what I'm trying to show over here. This is, again, the x-axis is time, y-axis is frequency, and this is what happens. Now, all this medium between the host and our galaxy is also filled with electrons. So similar to what happened to all this lightning signal which we saw on the other side of Earth, due to these electrons, higher frequency waves will arrive earlier on Earth as compared to the lower frequency waves. So what we see here on Earth is a signal like this, which is again swish kind of a signal which we just saw. Here is the first FRB ever detected. So here on the x-axis, we again have the time. And on the y-axis, we have the frequency. So this is 1.5 gigahertz over here. This is 1.3. And this swish, this black curve over here is the swish or the signal which we actually saw. Now, this dispersion or this whole delay, or how much delay there is between the highest frequency and lowest frequency, is dependent on how many electrons are out there. Okay, so we can use this to estimate the distance or how far the FRB is, and that's because we have some sort of a map of the whole galaxy where we approximately know, or we have modeled in which direction how many electrons are out there. So what we do is we do not know. We can actually measure this whole distance from the top part till the bottom part, and this whole distance will correspond and then we can measure the time difference and we can convert it to a distance, so we actually know how far the signal actually comes from. There's also, you should note something, that as you can see from this picture itself, our Milky Way galaxy is much more dense as compared to this whole medium in between. So it's called the intergalactic medium, or IgM. So our own galaxy also has electrons, but it has much more electrons as compared to this medium. So there's a small contribution from our own galaxy as well, which we can sort of disentangle. And then together, using models for both our galaxy and models for electron density outside our galaxy, we can use these together to sort of locate how far the FRB is. So this on the left-hand side is the first FRB. It's also called the Lorimer burst, named after my advisor Duncan Lorimer. Here on the right-hand side with his student David, who actually first found the signal. So these are FRBs, and now the question is how do we actually find more of these? So this is what they look like. So you have frequency on the y-axis, time on the x-axis, and this is the swish, the sound which you heard. What I'm showing here on the top of is if you add all of these frequencies and just leave all the time alone. So this is what it looks like. So this is the signal which we are looking for, except the signal is sort of switched, or has this delay between the highest and the lowest frequency. So we can correct for this, and this thing is called de-dispersion, or we can de-disperse the signal. So we can correct for this so that this whole thing lines up, and when it lines up, you can see the signal becomes much stronger. So this is what we have to do. We have to go out there, we have to look at look at the sky, see if there's a signal, de-disperse that, and then once you have a really strong detection, you can actually know that this was a real astronomical signal. So that's what we do. We Since the detection of FRBs, astronomers started looking at the sky, like, can we find more FRBs? And this is what scientists in general do. We try to see, are there more FRBs? And indeed, about 10 years down the line, we had about 30 to 40 FRBs, or maybe even more, I think 50 FRBs. So we looked at different parts of the sky with different telescopes and found more FRBs, uh, and even more FRBs when new telescopes started coming up. So telescopes like Utmost and Parkes in the Australia, the FAST telescope in China, the CHIME in Canada, and then Green Wang over here. So there are more telescopes all around the world started looking for FRBs, and then we started finding more and more of those. So the next question is, uh, this is what we do as scientists: ask very simple questions like, what are FRBs? Why are they? I mean, what's causing them? Why are they happening? And where should I be looking to find more FRBs? And if I look somewhere, when should I be looking? Because these are just cosmic flashes, so they just come and go like this. And when should I be looking? What's the best time to look for FRB? And if I look at one place for a really long time, how many will I see? And will I even see anything? Or will I be just staring at blank sky and not find anything? The last thing is, my telescope powerful enough to find more of these objects? Now, to answer all these questions, you actually need to do one thing, and that is just detect more FRBs, find more and more of these things, and only then you'll have a better understanding of them to answer these questions. But we'll try to answer sort of some of them in terms of how we can sort of find many and what we can do with them. So the other part, which of course interests scientists, is that what exactly are they? What astronomical phenomena or what physics is actually causing them? And this is not my area of expertise, so I just have one slide over here. There are different theories, and we have recently passed the stage where we have more FRBs than we have theories for FRBs. So uh, the popular ones include, there are magnetars. So these are sort of dense stars which have really high magnetic fields, which could be causing FRBs. There are black holes and their interaction with nearby objects, which could be causing FRBs. But as of now, we have no definitive answer towards what exactly is causing them. But now let's get to the topic, which is very near to my heart, which is how to search for more FRBs, how to find more FRBs. And the simplest, or this is what it's a very simple three-step process which everyone has to do to find FRBs. The first one is get radio data. So pick a radio telescope, get some data from it. So here we have the Green Bank telescope. And the second thing is you have to de-disperse that data. So you have to remove that effect of dispersion where higher frequency waves are arriving earlier as compared to lower frequency waves. So you have to get rid of dispersion, because as we have seen, once you de-disperse your signal, it becomes really, really strong. And I'll show you again here. So this is what our data looks like. Here on the x-axis, again, I have the time. On the y-axis, I have the frequency. And in this case, you can actually see some signal over here. In this case, the highest frequency is at the bottom, the lowest frequency is at the top. And if you add all of these frequencies up, this is what you get. And this looks like noise. This is why de-dispersion is important. So if you start de-dispersing the signal, so if you just add all of this up and put it here as a line, this is what it looks like. So this is, if you do not do any de-dispersion, that means it's 0. This is what it looks like. If you start de-dispersing it, but you're not at the right amount, you have not corrected it completely, this is what it looks like. But you can see that the signal starts to form. You can start seeing some signal over here. This has started to line up. And then once you line it up perfectly, you correct for all of the delay properly, it becomes a really, really strong signal which you actually can't miss. So this whole peak is so this whole time series over here can be seen in this line over here with this bright spot. So if you go above or below, your signal won't be properly corrected for, and hence you'll see a spread. So this forms like a bow tie shape. And this is what we use to find or to sort of detect more and more FRBs. And then once you have all the radio data, you de-disperse it at different values, correct for different delays, because you do not know a priori at what delay your signal would be. And then you create all of these candidates, and then you just look at them. It's a very simple three-step process. Get radio data, de-disperse it, and then start looking at the candidate. If it looks like this, it's a real signal. But more often than not, it's going to look like this. It's going to look like this, which may mimic the real signal, but it's actually a radar in this case. So you can see it's this sawtooth kind of waveform over here. This is what we actually already know. So this is what we call as RFI, or radio frequency interference. This is all the man-made signals which look like FRPs but are actually not real signals. And this is caused by a lot of things like radars, Bluetooth, Wi-Fi, and so many things. So that's what most of our job looks like. So here's a bit more a sort of zoomed in view of this radar signal. You can see there's this sawtooth pattern in this case. Now, this is what most of the PhD job looks like. You actually go to a telescope or an observatory, collect some data, make such plots, and keep looking at it. Now, there's a lot of variety which we have seen in FRBs in about last 10 or 15 years. And let's sort of talk about that. So most FRBs are one-off events. That means they do not repeat. So you look at a part of sky, you saw an FRB, it's gone, and then that's it. You keep looking at that part of sky again, you probably won't find the same FRB. But in 2016, we found something called a repeater. So one source was actually repeating just fine, because now you have two different kinds of FRBs opening more and more questions. Are there different kinds of FRBs? Do all FRBs show these repeat bursts? And if that's so, why have we seen this one repeating much more often than the other ones? Now, that's not the only thing. Some repeating FRBs are periodic also. That means if you go back after a certain time, you'll always see them on. So in this particular case, the FRB which I'm showing over here has a period of about 160 days. So if you go and look at the same part of the sky after every 160 days, you will see the signal again and again. So that opens a whole new set of questions. What astrophysical phenomena can be causing this 160-day periods? Now, FRBs look different as well. So there are ones where you only see this single peak, as you can see here. There are ones where you see this huge variation. There are multiple peaks present. There are some which are incredibly patchy, whereas some who are just present in the whole band. And yeah, so some of them are wide, while some of them are very narrow. Some of them are really strong, and some of them are really weak. So there's a huge variety, but all of these signals were extragalactic. What that means is that they were coming from outside our own galaxy until we found one which was also coming from our own galaxy, which sort of helped us uh, point more towards this whole magnetar theory. But this is what sort of the variety looks like. But now let's say you are a student and you want to find more FRBs. So what you'll do is you'll go to a telescope, get some data, make all those plots, and then start looking at them. So this is what your job looks like. So it'll be like, okay, is this real or is this noise? You're gonna say this is real. This sort of looks real, which is good. And then you'll see, okay, this is noise, more noise, more noise, more noise, and more noise. Because this is what real life looks like. You It's really really hard to find FRPs because until last year, when this Chime telescope in Canada found about 400 FRBs in 2 years, we had only found 130 or 150 FRBs in about 12 years. So it's incredibly hard to find FRBs, and that's what you'll be looking at, a lot of noise. And of course, if you're impatient like me, 3 years, 3 hours later, looking at noise, you'll be like frustrated. So what's the way out? And the way out is we make machines do it. Like, why should we sit and be doing this? We can do science while machines actually find more and more FRBs for us. And the way to do that is to use artificial intelligence and more specifically neural networks. And I'll be sort of talking about what neural networks are and how they work and how we particularly use them in this particular scenario. So neural networks are sort of these compute or these algorithms which are inspired by human neurons. Or so in a neuron, what you have is dendrites where you receive more signal. It travels to part of the cell body, and then there are axons on the other end which sort of transmit that signal to the next neuron. And this is similar to so we have sort of tried to imitate this by taking multiple sort of signals in, and then you apply some sort of mathematical operation on it, and then you just pass it on to the next one. You apply a lot of these, we exactly call them neurons. So you apply a lot of neurons and you try to simulate this whole this whole thing. Now what happens is that you can use these neurons or the set of neurons or neural networks to mimic any function or learn any function, and that's what we have done over here. So before we get into that exactly, just want you to also understand that any image which you see is just a matrix of numbers. So if you look at this digit 8, it's actually split. So you can put a grid on top of it, and then wherever it is black you can put a number 1, and then wherever it is white you can put a number 0. So this is how you represent, this is how we see all the images, or this is how we store images in our computers. So here's a really simple smiley. All you do is you put it on a grid and you put blacks and whites, and then just code them with ones and zeros. You don't have to code them with ones and zeros always. You can add more variations to it. So you can do things like this. So here is a digit 8, and the place where it's more white, you can represent it with a higher number, and the place where it's less white, you can represent it with a lower number. So with this 8, you can see this is the most bright part. These are the numbers which are close to like 255. This part over here is sort of grayish, so it's about 100, and then all the other part over here, which is and the bottom, which is black, is just 0. So this is how we represent numbers. This is how we represent images. These are just matrices of numbers. And then what we do is we take them and then we put them in a very special a special kind of neural network called the convolutional neural network, where we apply this operation called convolution, which I'll explain. And then we take these and then we ask the question: is it a real thing or is it a fake thing? Or you can ask, and you can do it in a very simple fashion as well. You can give it a picture of a cat and a dog, and you can ask it: is it a cat or is it a dog? And we'll see how that exactly happens. So we apply this thing called convolution. So on the left hand side, you have this image which is just made with ones and zeros, and then you have something called a filter over here, or kernel, which is 101 010 101, and then you multiply each value over here. So you multiply this one with this one, this zero with this zero, this zero with this one, and so on. And you multiply all of these 9 values with these 9 values, and then you sum them up, and then you put it in a new matrix. So this is what is called convolution. And what happens after convolution is that you can actually extract features out of this image. So you can, and then you slide over, you go to the next part of the image, and then you do the same thing. So it can actually be shown over here. So you have, again, this green thing is your image, this yellow thing is your filter. So 101 and 010 101, the same filter over here written in red. You multiply each value, add it up, and that's what you get. At the end, you get a new image, which is called the convolved image or the convolved feature, and then you can apply many of these filters to extract information out of your image. And then you slide it along. So you keep moving towards you sort of pass over the whole image and create a new image out of this. So this is how we extract information out of an image. And once that is done, you can actually do it multiple times. So this is what it looks like. You take a digit 3 over here, you keep applying convolutions to this, you extract features, you extract more features, until at the end you have just like 10 numbers which are gone from 0 to 9, and then one of them will sort of say 1 and the others will probably say 0, telling which digit it was. So these are called convolutional neural networks, and this is just another way of sort of showing them. But the question is, okay, we have this concept of convolutional neural networks. How do we use them? And the way to do that is you actually train them. What you do is you give them a huge amount of data. You give them huge amounts of data, and then you ask them to learn on its own. You don't have to sit and learn these. You don't have to sit and make these convolution kernels. These networks will learn it on your own. So let's see how to do that. So we take a CNN or convolution neural network. We give it an image of a cat. I say, here's a cat. Learn that this thing is called cat, and it's gonna take in this image, pass in through the network. Okay, and then it can only tell you whether it's a cat or a dog. So it's gonna say, let's say it's a dog, and then you tell the network that, oh, okay, no, it was a cat. So it's like, okay, I'm gonna take that information and I'm gonna try to tweak things in my network. It's called modifying the convolution filters or kernels, and then I'm gonna try again with a new image. So you take in a new image, you have a new image of a cat, you again do the same thing, you pass it through your neural network, and then it's gonna say maybe it's a cat or maybe it's a dog. I'm not really sure. It's like 50-50 for me. And it's like, okay, you're getting better, but it's actually a cat, so you need to learn that. So it does the same thing again, you modify it again, you give it another picture of a cat, it again tries to learn it, and now it says it's a cat. Yep, and now your network is working. Now what I've shown you here is just like 3 images of a cat, and it sort of learned. In practice, you do it with like thousands of images. So you give like 1,000 images of a cat and 1,000 images of a dog, and then maybe your network will learn how to call it a cat versus a dog. So this is how we train our neural networks, or a convolution neural network in this particular case. So this is what we exactly did. We created convolution neural network which take in these images. So it takes 2 images. One was that signal which you saw, and the other one was the bow tie, which I was showing you earlier. So you take both of these images, you pass it through convolution neural network, and then you ask it to learn which ones are real signals and which ones are the fake ones. And then we did it over about 40,000 of images. It took us about 3 months to make this. But then once we were sort of satisfied with the performance, the final network sort of does this. So it can actually find more than 99.5% of all the FRBs which we gave it. So it's incredibly precise. It works really well, but that's not the only thing. The other thing is that it works really fast. It can classify up to 50,000 candidates per hour. And that's much more than any human or an army of humans can actually do, because humans will eventually get tired, but this can actually keep running all the time. So we have this neural network which we call fetch. It can take in all these candidate plots. It can tell you whether something is real or not, and it's going to be correct 99.5% of the time. So of course this actually made the news. So multiple sort of news websites and covered us, and we now actually have a neural network which can make everyone's life easier. You can just go back to doing science while all of these networks for us actually sit and find more and more FRBs. So we took this and we tested it across multiple telescopes across around the globe. We tested it on Green Bank telescope here. We tested it on VLA, which is the Very Large Array, on the Arecibo telescope, GMRT, data from ASCAP in Australia, Urumqi in China, Lowell in UK. So it doesn't matter which telescope your data came in from, or fetch can actually classify all these can actually classify which ones are real signals and which ones are not. So the next thing then is to take huge amounts of data, search for FRBs, and give it to fetch, and then just ask it to classify and find more and more FRBs. Well, that's exactly what we are going to do next with the petabyte project, and the aim is that we have all this archival data sitting on disks all around the globe, which is more than 10 petabytes. It's going to generate more than 15 million of candidates, and humans will probably take about 6 months to get through it. And if you just give it to fetch instead, and the amount of time it takes to find FRBs in 15 million is about a week. And if you have more computers, you can scale it up. It's gonna take even less time than that. So uh, this is sort of the summary slide. We started with what the electromagnetic spectrum is, but the visible part, which we are usually familiar with, and then we went to the radio. We see how different parts of electromagnetic spectrum encode different information. Then we talked about radio telescopes in particular, going back to FRBs, how we use radio telescope to find them. This is what a signal looks like, the swish over here. There's a huge variety of those, but it also takes a huge amount of time for us to sort of sit and look through plots. So the idea is to use AI or artificial intelligence. In this case, our software is called Fetch, which is now being used to find more and more FRBs. So this work was not done alone. It's done with a whole team of people here at West Virginia University. So this is work done with Chitij, Nate, Dunk, Joseph, Sarah, and Maura. And I guess I'll be happy to take questions now.
All right. Thank you, Devansh, for sharing your first-hand experience and your detailed explanation. I think given certain kind of a insight to the people who are interested in this field, and also help them in the way like how to move ahead if they want to pursue this as their passion into their profession. So we have one question from
Yep, go ahead.
Parth. You can see on the screen, do all the bursts from the repeating FRBs occurs in small bursts or do they occur over large period of time?
So yeah, let me put in a time scale for you, and then you can decide if it's small or large. For repeating FRBs, we typically see hundreds of bursts in couple of days. Now these bursts could be, they're not spread out evenly within the spread of days. So sometimes what can happen is you are looking from a telescope and you found 30 of them in like 5 hours, and then you didn't find anything for the rest of the day. So this is what typically happens, and we I mean, given that, for example, for the repeating FRB which I was showing you, it's 160. It stays off for 160 days and then turns and then comes on for like few days. You can put it in context and call it either long or short. That's totally up to you.
I hope Parth you got your answer. In case you need other clarification, kindly drop your question in the chat box. So we'll take the next. Manoj Jagannathan. How many training images were used to train the CNN?
So
Training
we
C.
used 40,000 images.
So, participant, I request you can drop your questions related to the presentation. If any clarification or doubt you need to get clarified, you can put it in the chat box. We can take some of the questions because we do have time. Thank you for the wonderful lecture. Nice talk.
Thanks, everyone.
I think we have no question. Okay, we have one question. Do
Do
radio
radio waves
waves
travel
travel?
forever?
Travel forever.
Yes, I guess. I mean, unless they're absorbed by sort of something that they just sort of do.
Right, we have. I don't think there is much question in the chat box. So, before closing it, I would like to take a last comment from you, Devansh. Like anything in particular related to the research area you would like to suggest undergraduation or a post graduation students to go ahead in this field. So, I think would be a great help for them.
So yeah, I mean, most of the undergraduate fields are have now started incorporating some sort of curriculum for AI now, which is becoming the new sort of the new big thing. So if your undergraduate curriculum has it, do take full advantage of it and learn all about it. Because it's everywhere now. It's starting from your phone to everything which you're using today is now being impacted with AI. So the earlier you start learning about it, a couple of things. One, you can start contributing and start knowing what it can do and what it can't do. The other thing is you can also learn about all the biases which are sort of coming in because of all this. So I'll give you a very small example. You probably already know this. You plug in your phone at night and it tells you this is how long it's going to take to charge. um, and you would think that's a very simple thing to do, but what actually your phone does is learns when you usually charge your phone and how best to charge your phone based on that criteria or based on that time frame which you always charge your phone on, so that you elongate your battery life. And it actually uses a significant amount of AI for that. So it's a very small thing which you usually don't even think of. And then there are all these things like Google Lens, where you can put, take a photo and it's going to tell you what object it is in. I'm now these days working in the medical field, so you use it for detection of things like cancer, or more efficient detection of things like cancer and so on. So this is the new hype, and it's going to stay here for at least 2 or 3 decades. So get on it early, I'll say.
Very well said. So we'll take with this. We'll take last question because the gentleman posted in the chat box, and then we'll wrap up the session. In terms of the
S-
CNN and data engineering, was the quality of the radio data image a key factor?
Yes. So your models are only as good as your data is. In case of the images which we made here, we had really high resolution images available to us, so we were really lucky in that aspect. Um, so yes, that does always play a key role in how good your CNN turns out to be at the end.
I think with this, we'll wrap up today's session and really look forward for your participation in other ventures organized by the planetarium. On the behalf of Planetarium, thank you, Devansh, for coming here and joining in and sharing such a first-hand information and very well put together thoughts during the discussion. I think that this has given participant a big insight how the artificial intelligence is peeping into the cosmos and also our daily lives. So thank you for joining in and sharing this lovely presentation with the participants.
And thanks for giving me this opportunity. Always happy to uh, talk at Planetarium.
Really, we really look forward for such other ventures in the future. Thank you so much. Thank you, participants, for joining. Bye and take care.